Okay. To talk about volcanoes, first thing we need to talk about is what makes a volcano. Well, volcanoes are made mostly of magmas. Okay, magmas that have swollen up and have formed many layers on the earth. Well, let's talk about this magma before we talk about volcanoes. Okay, first off, where do we get magma? Well, magma forms in the asthenosphere when solid rock melts. Magma is melted liquid rock. That should make sense for you. Okay, well, how do we melt magma? Well, you need heat, you need pressure, and water. These are the three things that kind of give us the magma. So this is our quick outline. So basically, what's in volcanoes? Magma. How do we get magma? Well, it's got to get melted rock, and that depends on heat, pressure, and water. Okay, I have 2 slides to explain this. Okay? Heat, pressure, and water influence the melting of rock, which gives us magma. Okay.
Wait.
Okay, first let's talk about heat. The mantle's really freaking hot. Gentlemen in the back. The mantle is really hot. Really, really hot. We're talking, what, 14 to 1600 Celsius hot. Okay, this rock is just about at its melting point as it is. The only thing that's really keeping it from being melted, mantle, is the fact that it is under an extreme amount of pressure. Okay, so this rock is just really close to being melted. And sometimes it does cross that barrier and it melts. Well, if you want to fully melt it, you need a little bit more friction or a little bit more heat. You add one of these two, you're going to get some magma instead of just lithosphere rock. I'm sorry, I said that wrong. Asthenosphere mantle rock. Okay? Friction for plates moving, right? You know, the old, thing. If you rub your hands together, you can feel the heat, the friction. Gentlemen, I expect you to be adults in this room.
That one in your hand.
Come on. Okay. You guys. Won't be that kind of a day. Okay. So you need a little bit more heat to melt these rocks, to get magmas. You also need pressure. Well, I just said that it's the pressure of the earth pushing down that's holding this mantle in a solid state. Well, if you take away some of the pressure, the mantle has the freedom to go, it takes a big breath, and it goes liquid. This is called decompression melting. So what you should be writing down in your notes, decompression melting. When you take away pressure, it allows it to melt. And you get magmas, liquid rocks in the mantle, or in the asthenosphere. Okay. I said it depends on heat, pressure, and water. I combined the pressure and water slides because mostly it's this. Water helps things melt. The water content changes the melting point of things. If you add water, water is not compressible, so that changes the pressure of things. So it just, for the generalness of it, we're going to say, if you take away pressure, you get melting. If you add water, you get melting. Pretty simple concept, right? If I want to get magma, I increase heat, take away pressure, add water. If you want to get magma, you increase the heat, or you could take away the pressure, or you could add water, or maybe a combination of all three. Okay? So now we have magma. What is magma?
Magma is melted solid rock.
Melted rock. Okay. You have that, Jenny? Do you have to understand the concept? You take a rock and you make it really hot. You make it really hot. What does it do? It melts. So you have that concept? So if we take a rock, under the earth and it gets really, 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 really hot and the temperature continues to increase, what's it going to do? It's going to melt. Melted rock is called what? Magma. That's the biggest point I want you to get right there. Okay. The reason a lot of those rocks don't melt is because if you put pressure on things, it tends to hold it in a stable state of solid. Okay. You might be thinking that water doesn't act like the way. Water doesn't act that way. Water is the one thing that's different. So we can throw water out the window. You hold pressure on something, it holds it as a solid. Just believe the fact, okay? If you take away pressure, the solid stuff allows it to melt. Does that make sense? Okay, that's what I want you to know. Right? You guys have this? Now's your time for questions. Moving on. Okay, so next thing we're going to talk about is here we have these magmas, these liquid rocks that have melted from increased heat and decreased pressure. Well, magma's liquid rock. You have liquid rock in the inside solid rock. It's trying to escape. So it's doing its best as it can to get out of the earth. Similar way that if you have a soda, you put a soda there and you pour it into a glass, what do all the air bubbles in the liquid do? They go up to the top, right? So the same thing with liquid in a solid, it moves its way to the top. In this case, the magma. Now, there are 3 places you get magma showing up. And this is a good thing, because you can actually plan your life around how you never have to interact with magma ever. Okay? Lesson 1, don't live near a convergent plate boundary. Lesson 2, don't live near a divergent boundary. And lesson 3, stay away from hotspots. We happen to know where all these are, so if you want to see magma or want to stay away from magma, if you know where the convergent plate boundaries, divergent plate boundaries, and the hotspots are, you either will see or will never see the magma escaping the surface. As far as I'm aware, there's nothing in Virginia. So you're safe. Right? Because Virginia is not on a convergent, divergent boundary or a hotspot. So the east coast of America, whew, we're good. West coast of America, not so much. Okay, so here's a nice pretty map that's way too complicated and complex for you to understand with one glance. But that's okay because I'm going to take it one picture at a time and I'm going to break it down and explain what's going on. But basically you've got, here's the subduction magmas. Here's your divergent magmas. And then here's your hotspot magmas. We've talked about these 4 already, these 4 pictures. This was all of plate tectonics. We were talking about divergent boundaries, subduction zones. Okay, that was a good part of plate tectonics, so hopefully this will be a nice review. We have not yet really talked about hotspots, so that'll be a fun talk. So let's review really quickly divergent volcanism. All right. The plates separate because of the convection underneath. The convection pulls the plates apart. Oh, wait. What drives convection? What makes convection work? Here's something that you should write down in your notes.
Convection.
Okay,
What makes it work?
What makes the convection happen? What forces the convection current?
The heating and cooling of
So I would say, what drives the process? Heat. Okay, so you guys should write down that for this, all the volcanisms, what's driving the process of the convection that's bringing the hot stuff up? Heat. Okay. Specifically, in our case, heat from the core of the Earth. Okay, but we've learned about divergent volcanism. What kind of magma is there with divergent volcanism? This is important. Dietrich, what kind of magma do we have with divergent volcanism? Basalt. Guys, you see how I'm giving you this term over and over again? Wait a second. That sounds like a great testable concept, right? Divergent volcanism is always basalt. Now, why am I harping on this? Well, because the type of volcano associated with this will have basaltic magmas and lavas, which is going to influence what kind of threat it's going to be or what kind of features it's going to have. Okay, so here we have some locations for Divergent, the Atlantic, and the Rift Valleys. So this is all review. Okay, so here's a pictorial review of what we just did. You have the upwarping and the cracking and the spreading. It begins to completely separate. The crust starts to, instead of being continent crust, it becomes ocean crust. So this ocean crust is here, continent crust here, it starts to spread, and it goes to finally an ocean basin. This is exactly what happened to the Atlantic Ocean. I want you guys also to remember a couple numbers. What is the density of continent crust? Density.
Oh.
It's a number.
Continent is like,
And it's in grams per cubic centimeter.
is it 3?
It's not 3, it's
2.5.
2.7. You do need to know that. That's a test question.
Yeah, I need questions.
What's the density of ocean crust?
3.2.
3.0, you're close.
Hey, man.
Okay, if you can't recall these on like, boom, Mr. Cork, this is what it is, then you need to learn it because, promise you, test question. How do I know this? Because I just looked at the test. I helped make the test. Okay, test question. You've got to know what the densities of continent crust is. Oh, something else you have to know. What is continent crust made of? What kind of rock? Starts with a G.
The continent crust.
Granite. These are made of granites.
Alright, good.
How about these ocean crusts? What are the ocean? Basalt. Good.
Okay. I already said it.
This greatly influences what kind of volcano it's going to become. So you have to know these facts, right? You have to know that heat drives convection. You have to know the densities of the two different crusts, and you have to know what the crusts are made of. Okay? You guys have that written down? Now would be a great time to just write that down and kind of absorb it in your brain and say, Mr. Cork said this is important. I want to get easy points on the test. I want to understand the content later. Go ahead and force yourself to memorize 2.7, 3.0 granite basalt. Okay? You guys let me know when you're ready to move on. Okay? Does anyone need time to write this down? Check. Are you good, Scope? Okay, so this is divergent volcanism. Here's a picture of where we see divergent volcanism. Right? Oh, look. Here's all the mid-ocean ridges. The one that's really famous and everyone knows is the Mid-Atlantic Ridge. It's the longest one directly. But do you know that they're all connected? Do you guys see how these are all pretty much connected? The longest chain of mountains on Earth are the Mid-Atlantic or the mid-ocean ridges. Okay, so all along these plate boundaries, we're going to expect to see volcanoes that have basalt. Does that make sense? Because they're basaltic lavas. You can see, what island is this here? It's the island next to Greenland. Iceland. Iceland is a giant volcanic hot zone, so to speak. It's got lots of volcanoes. It's on a divergent plate boundary. That shouldn't surprise us. There's a place in Iceland where you can step on one side and step on the other side, and there's kind of a crack in the middle, and that's actually, you're on the European plate and the North American plate, and if you stood there a very, 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 very long time, your feet would just get further and further and further apart. You can step on both sides of the plate because you can see the plate boundary runs right through Iceland. Iceland will continue to get bigger. Okay? Now, that's all divergent volcanism. Let's talk about convergent volcanism. Convergent volcanism. Okay, really quick. The plate sinks, you get water, you get magma, you get volcano. Okay, so let me go back in case you want to write this down. The plates sink, water gets squeezed out of the rock, that helps it melt. You get the magmas rise to the surface like bubbles in a soda, and they pop on the surface, so to speak, and that gives you volcanoes. For example, the Japanese islands, the Aleutian Islands off Alaska, that would be ocean to ocean. Ocean to continent would be the Cascades or the Andes Mountains, and there's other examples besides that. Yes? You need to know the difference between ocean to ocean. Like, the ocean to ocean gives you the volcanic islands. Ocean continent gives you continent volcanoes. The difference between the Andes mountain range on South America versus Japan. You should know the difference. Okay? Do you guys back there understand the difference?
Yeah.
Okay? Table over there, you guys good?
Yes, sir.
Mary, you good?
You sick?
Okay.
You know what I'm saying.
So this is convergent volcanism. You need to know the differences between these two. Shh, 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 shh. Okay? So, what is this? Which one is this? Ocean to continent or ocean to ocean?
Which one?
What is it?
Ocean.
Ocean to ocean. And it develops a volcanic island arc as opposed to a volcanic continent arc, or continental volcanic arc. Okay? Both cases make volcanoes. The difference is the volcanoes here are almost entirely made of basalt because nothing's coming up but basaltic lava because that's what's being melted here. Here, on the other hand, the lava and the magmas that come up mix with continent crust, and you start getting a lot more intermediate and felsic lavas, and the volcanoes here tend to get pretty booms. Right? They're explosive, they're very violent. Okay. Ring of Fire! Raise your hand if you've heard of the Ring of Fire.
Fire was supposed to come out like from the side.
Besides the notes, has anyone heard of the Ring of Fire before the notes? Okay. The Ring of Fire encircles which ocean?
Atlantic. All of All of it.
It's the specific Pacific. Okay, the Pacific Ocean. The Pacific Ocean is getting smaller and smaller and smaller as the Atlantic is getting bigger and bigger and bigger, right? Because the Atlantic is a mid-ocean ridge, it's expanding. Look at all these subduction zones all over here. The Pacific Ocean is getting smaller. All these plates are getting smaller. Now, that being said, any place you have an active plate boundary, like there's a place here in Mexico, Central America somewhere, where a guy had a cornfield. He literally went outside and a volcano grew up inside his cornfield. It's a pretty famous story. Volcano's still there. Cornfield is not. Okay, go down here. You have the Andes Mountains. There was in Chile, there was an earthquake that was 9.1, 9.2. Huge earthquake. Subduction zone. Okay, come over here. Krakatoa, Indonesia. Okay, the Christmas tsunami of 2004, I believe it was, killed 100,000 plus people. That happened right here. Subduction zone. Japanese earthquake 9.0, just a couple of years ago. It's very recent. It's in your textbook, but it's very recent. Okay, subduction zone. This is an entire chain of volcanic islands. These are the Aleutian Islands. Subduction zone. You guys seeing that all the dangerous places to live are along the Ring of Fire? Why is it called the Ring of Fire?
Because of all the volcanoes.
Because of all the volcanoes. Okay? Volcanoes tend to be kind of hot and fiery.
Wait.
I mean, Mount St. Helens blew up this part of the Northwest. It's on a subduction zone. You don't see this particular one here, but this is a subduction zone.
Wait, so Since if you say the Pacific Rim is smaller, does that mean like North America and Asia can touch again?
Potentially, maybe. I don't know. I mean, you're talking about 250 plus million years in the future, so I know that North America is kind of shifting this way. There's also there's a mid-ocean ridge here that's separating here, so there's a lot of factors that go on. So it's possible, but I haven't seen the projections recently. Okay, so what is this thing called?
Ring of Fire.
The Ring of Fire is around which ocean?
Pacific.
Okay. Is it safer to live on the East Coast or on the West Coast?
East side.
Why?
Because it's not on a subduction.
You're not on a subduction zone. You're not on any kind of an active or passive margin here. You're just kind of like, woo, safe. So you don't have to worry about big earthquakes. You don't have to worry about volcanoes. You don't have to worry about a lot of things. Yeah.
Remember you said last class you got to us why we had an earthquake?
That's really for next class, but why did we have an earthquake here? That's really for next class. It's for mountain building. Okay, let me save it for there, because if not, I'll get completely off topic. I can't afford to do that today. Okay, so you guys get the Pacific Ocean? Okay, this is all convergent volcanism. Okay? Now we're going to talk about intraplate volcanism. Okay, forget the title. We're going to talk about hotspots. Okay? Hotspots. First thing I'm going to show you, let me show you the most famous hotspot in the world. Hawaii. What do we notice about the location of Hawaii?
It's in the middle of the fire.
It's smack dab in the middle of the Pacific Plate, or in the Pacific Ocean. So Hawaii is nowhere near a plate boundary. But yet, what are the Hawaiian Islands made of?
Volcanoes.
Volcanoes. So yet we can have most of the volcanoes are around the Ring of Fire. Some are in a few other places. These aren't the only volcanoes, but this is where most of them are. Okay, but yet we have a few of these hot spots that it's like there's a hot part of the mantle. We're not sure why. We have some ideas, but for pretty much it's a hot part of the mantle that it gets so hot it burns its way through the crust and makes volcanic mountains. Okay? Sometimes. And sometimes it's not always a volcanic mountain. But Hawaii is a beautiful example. Okay, so it's an area where the rising magma burns through the crust. Not associated with plate boundaries. Okay, not normally associated with plate boundaries. You might occasionally get a hot spot under a plate boundary. Iceland is debated. Maybe Iceland's a hot spot, but plate boundaries, not plate boundaries. Okay? Typically, basalt lava. Hawaii is a great example, and the Deccan Plateau is another good example. Has anyone heard of a place in the United States where you can see all the bison you want with a few wolves and some moose and some geysers?
Yellowstone.
Yellowstone. Yellowstone is a hot spot as well. Yellowstone is also called a super volcano. It's a hot spot, people. Okay. But it occasionally erupts and destroys half the world. Okay. Is that? Very occasionally. Like every 300,000 to 400,000. Don't worry. Okay, so hot spots are these, it's not boundary volcanism, it's somewhere else. Do you guys have any questions on the basics of hotspots? Okay, pictures. Pictures are worth thousands of words. Okay, here we have that rising mantle. It gets to here, it's lost pressure, it decompresses, because if you take the pressure off it, melts. The rising magma, like a bubble in a soda, comes up to the surface, burns its way through, and we get layer upon layer upon layer upon layer of lava. Well, guess what's really cool? If you see lava that's exposed through the ocean, it instantly cools. And it makes these weird, like, tubular shapes. It's called pillow lava. It's not something you want to lay your head on, but it looks like these pillows everywhere. Okay?
Is it freshwater or the rock that's
What was that?
Like the rock that's formed from lava cooling.
Well, lava when it forms underwater typically is pillow lava. Typically. Not always, but typically. Okay, now this is if it's under the ocean, so this is oceanic crust. What if it's continental crust? Well, same concept, except now that this magma comes up through this basaltic rock, now it's coming up through granitic rock. So some of the magma takes on the characteristic of this high silica rock, granites, and what you get on the surface is a little bit differently, but you still get flood basalts with hot spots. So, basalt, woo! Yeah. What kind of rock is basalt? Rich in iron, oceanic rock, right? Okay, so this is the Deccan Plateau. The Deccan Plateau, I don't know if you've heard of it. I hadn't heard much about it, but it's in India, which is probably why I hadn't heard much about it, because I don't go to India very often. Okay. Eruptions. Now we're getting into the fun stuff. Okay. What causes a volcano to be Dante's Peak and make a movie out of it, right? What causes it to be explosive? The characteristic of the magma and the amount of dissolved gases. Well, this is kind of, I really simplified this down for you. Here's the thing. It's all about the silica content. The sad thing is I dropped it before I caught it. Okay, it's all about the silica content. The higher the silica content, the more viscous the lava becomes. The more viscous the lava becomes, the more gas it holds. The more gas it holds, the greater the explosive ability of the gas to try to escape. So, the more silica it has, the more viscous it becomes, the more gas it holds, and that tends to form more what we call pyroclastics, or ejected rock materials, like giant rocks the size of houses and cars, and some of them are really small and fine like ash, and some of them are a little bit more like sand. You know, so this range of ejection stuff gets greater and greater and greater with the higher silica content. So the characteristics of the magma, you want to know how high is the silica content. Well, guess what? Basalt isn't very high. We're talking about 50%. The higher you go to andesitic, andesitic just means intermediate, so this would be mafic, intermediate, felsic. So the higher you go toward the granites, the more and more silica you have, the much more of a boom you're going to get. Okay? Okay. We're going to talk about viscosity and gas content in a second. What I want you to write down in your notes right now is when you write down characteristic of the magma, you're going to write more silica, more boom. Okay? More silica, more boom. Parentheses. Okay? And that adds to the amount of dissolved gases. So the biggest thing that you need to know is the more silica content in the magma or in the lava, the more explosive it's going to be. Okay? Eruptions. The more silica is in the magma, the more of a boom it's going to have. Period. Moving on. Okay. Can I move on? Okay. Viscosity. We got to talk about viscosity. If you don't say it with the New Jersey accent or a really bad New Jersey accent, it's no fun. Viscosity. Now, viscosity, the definition of viscosity is the substance's resistance to flow. Okay, so write down a substance's resistance to flow. Now, that's the definition. How do we understand viscosity? How does water flow? Really easy and fluid, right? Water flow. Could I do that with maple syrup?
No.
Well, I mean, it would come out, but it would be kind of goopy and gunky, right? It would flow really slow because it's more resistant to flowing. So maple syrup is more viscous than water. Okay? So without pouring maple syrup all over the room and making a huge mess, please understand that the syrup you put on your waffles and your pancakes is much thicker than water, right? Okay? It's more viscous. This vocab term time. So guys, if anyone has trouble with vocabulary, I don't care who you are, now would be a great time to write down viscosity, or something that's viscous is more resistant to flow. How does this affect magma? Well, magmas that are more viscous trap things in them because the gases can't escape, because it's more resistant and holds it together. So something that's more maple syrupy, or has anyone heard the phrase, "You move as slow as molasses in January"? Okay, because the colder you get maple syrup, the slower it flows. So I'm going to reverse that. The hotter you get maple syrup, the faster it flows. Has anyone tried to pour honey out of a jar and it's just kind of gloopy? But if you heat it up in the microwave or on a stove for a few minutes, now it's really runny. If you add heat, it lowers its viscosity, and then it flows better. Okay, so what is viscosity?
Resistance to flow.
Resistance, or the heaviness of it, right? It doesn't want to flow. The thicker it gets, it's more viscous. Well, what happens if you add heat to the substance? It gets less viscous. It flows better. Okay? The higher the silica content, you see how I'm trying to emphasize the silica here?
Yeah.
The higher the silica content in the magma, the more viscous it becomes. The more thick, the more resistant to flow. Well, which rocks are more silica prone? The felsic rocks, the granite rocks. Granite rocks are explosive because they have more silica. The silica makes them more viscous. Okay? The salt lavas, we're going like from 70% silica to 50% silica. These things just tend to be very flowy lavas. They flow really beautifully. Okay? Viscosity. It's very fun to say viscosity. Does anyone have questions on viscosity and how viscous something is? What is the one determining factor that can really change viscosity? Actually, two determining factors that change viscosity: heat and silica. Heat and silica. The frantic writing of the last few notes. Okay. Remind you guys that this is on School Fusion. Please check your School Fusion. Don't be like the one student. I don't check my School Fusion. Who do you think I am? Students. Okay. Check your School Fusion. I put all kinds of cool stuff there. Okay. Dissolved gases. Okay. The higher the silica content, the more viscous the lava becomes, the more dissolved gases it will have. Because a dissolved gas, well, a dissolved gas is gas that's in the magma that hasn't been able to escape. Carbon dioxide, water. So these are your two typical ones. There's other ones out there. You have sulfuric acid mixes in, you get sulfur dioxides and methanes, and there's a ton of dissolved gases. But you get a lot of water and a lot of carbon dioxide. Like 70% of a volcano's gas eruption is water. So, lots of water, lots of carbon dioxide. Okay. Well, what did I say happens when you take pressure off of lavas, off of mantle rock? Yeah. What is that called? Decompression melting. If you take the pressure off of something, it allows it to expand, and in this case, turn into a liquid. Okay. Now, when you do that to a liquid, when the liquid gets closer to the surface, it allows the liquid to expand even more, and those gases are allowed to escape. When you have less pressure, more gases escape. Well, the greater the viscosity of the magma, this prevents the gas from escaping early, and thus you get explosive granites or less gassy, less explosive basalts. Have I emphasized this point enough yet? What kind of granites are, What kind of rocks explode?
Yes, granite.
Granites. What kind flow? Basalt. Okay, these are all guesses. All right. Now this is where I get to show you pictures of Pahoehoe.
The hoi hoi?
Okay, everybody say this with me. Pahoehoe. Hoi. It's not Pahoho. Okay, it's Pahoehoe.
Is it Hawaiian?
It is Hawaiian. This is the Hawaiian term for really runny, ropey lava. It runs and flows like water. Okay? So here's a question for you. If you have lava that flows like water, Pahoehoe, is it more or less viscous?
More.
Less.
It's less, because the less viscous, the more like water. The more viscous, the more like maple syrup. Okay? Or, and other things. Here are two examples of lava. Pahoehoe, which is always fun to say, Pahoehoe. Okay? Flows like water. This. Now this is on Mount Kilauea in Hawaii. I love the Hawaiian language. It's all these like really powerful vowel sounds. Okay, now slower moving basalt lava that's rough and jagged. Do you see how this is different lava, guys? This lava is not stationary. This lava is actually creeping forward, but it's like boulders are constantly being pushed forward.
Are they running or are they chilling?
Yeah.
I have never figured that out. They're like,
Right, like you just, yeah, you know, explosives happen.
we'll put it this way, that they could walk away. You can walk away from this. You cannot walk away from this. This is like a river coming down the hill. This is like a very slow-moving avalanche. Right? It's not the avalanche that goes crazy. It just kind of like creeps along.
Like they just took a good picture.
Okay? This is Pahoehoe. This is a-a.
What?
Right? You know I said Hawaiian has these great vowel sounds? Pahoehoe. A-a. Okay?
Let's go to Let's go to like. Let's go to
It's like lava.
But do you guys see how this lava is actually coming and taking over the world at this point? Okay, so these are different volcanic materials. So these are lava flows. Volcanoes have lava flows. They also have pyroclastic material. Okay, pyroclastic. Let's break this down because I think words are easier if we can break them down. Pyroclastic. If I say you're a pyromaniac, what does that mean? It means you're way too happy with fire and I'm really scared that you're going to burn down the house, right? Pyroclastic. So pyro, fire. So we can say, we'll even write it in red, fire. Wait a second, where have we seen the word clastic before?
Rock.
Rock, pieces of rock. Or rock pieces, okay? So this is like rock pieces. We'll go with that. So if I'm talking about fire rock pieces, does that kind of describe pyroclastic material?
Yeah, very like hot rock.
It's practically fiery rock. Okay, well, pyroclastics are rock pieces that are thrown from volcanoes. Okay, so lava fountains, and it truly looks like a lava fountain. Okay, now what this does is it builds up a cone around the volcano because as this hot magma is being spewed off, so you'll have your volcano, okay, and it's spewing off hot magmas. Where do the magmas fall?
Gillette?
Where do these? You see where these magmas fall?
Yeah.
And it just builds the cone up around the volcano, where that is coming out. It kind of looks like a hot red inflamed zit on your face, right? It gets everywhere. All right, then you have dust and ash. Now, the difference between lava fountains and dust and ash is that when you throw ash, gentlemen, when you throw ash into the atmosphere, even up into the stratosphere, that gets into the sky and gets spread out, and it can cover thousands and thousands and thousands of square miles. Mount St. Helens had ash that went like a state and a half, 2 states away. The last time that Yellowstone erupted, it had ash that covered the entire western half of the United States all the way down to Texas. Okay, thus they call it a super volcano. Okay, so ash and dust can go pretty far. There's a volcano on Iceland, and it erupted just a couple years ago, not very long ago. And it erupted and it erupted, and it was a really long eruption because not all eruptions are burp and done. Some of them last months, if not years. Kilauea is still erupting, and it's been erupting for years and years and years. Okay, so these eruptions can go on. Well, this volcano in Iceland was throwing up enough dust and ash that they literally had to shut down all flight travel out of Europe because plane engines do not do good when you have small pieces of fire rocks entering your engine. They tend to get destroyed and planes like to crash. So that was bad. So we have to watch out for dust and ash. Then you have blocks and bombs. Okay, blocks and bombs. These are the larger pieces of this lava. They can be like house to car size, depending on how far you are from the volcano. But it can spew out a giant rock. Well, I mean, there's enough force here. It spews out a huge rock. I hope it doesn't hit you, right? This is why you don't want to be near a volcano when it erupts. And then you have these giant pieces of rock falling places, and they call them bombs because they are fire rock pieces. They're glowing through the air, right? If it's a block, it's not on fire. It's not glowing. If it's a bomb, it is. Blocks and bombs. Okay? So that's pretty simple, right? Stuff that comes out of volcanoes is on fire. It's fire rocks, pyroclastic. Do you guys have any questions about pyroclastic? Okay, now these are the pieces that are coming out. There's some other cool stuff that happens as well. But before we get there, we need to look at now, okay, there are 3 types of volcanoes. 3 types of volcanoes. Isn't this an exciting lecture? Everyone's asleep. Wake up. Okay, 3 types of volcanoes. Okay, the first type of volcano, this is your typical volcano. Okay, we'll start here. Magma chamber. Down deep below the volcano is an area where there's a lot of magma that's building up pressure trying to get out of the surface. As more and more magma is coming in here, it would be similar to you guys, man. I have to pee, I have to pee, I have to pee. Your bladder's expanding because it's filling up with urine, right? And before you know it, you're exploding out in the bathroom, peeing like a racehorse. Right? You kind of laugh, but that's what's going on with the volcano. It's filling up with magma, and the chamber is only so big, and the chamber is starting to swell and get pressure, get pressure, get pressure, get pressure. Well, it's going to get rid of the pressure in the weakest area possible, which typically is the vent of a volcano, and then it pees out all of its magma, for a nice graphic way of thinking about it. Okay? And then the magma chamber will depressurize, the volcano will stop erupting. Well, usually that comes out the main vent, but you can also have, you can have side vents as well. Mount Shasta has like a side volcano growing out of it. Then you have these layers of lava flows and layers of pyroclastic. So you have like lava and ash, and lava and ash, and lava and ash, and you get these layers, 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 and eventually this builds up a cone. Okay? This particular type of volcano is called a composite cone. So composite volcano, composite. Composite means more or one type of something put together. So here, the more or one type of something put together is, okay, you have your ash, your lava, your ash, your lava, your ash, your lava. Okay, more than one type put together. Okay? Do you guys have the first type of a volcano? Alright? Your second type of volcano is called a shield volcano. Shield volcano, well, it's big and broad and it looks like a shield. This is not a composite volcano. It only has the lava flows. So, Hawaii. This is Mauna Kea. So this is part of Hawaii, one of the islands, one of the volcanoes. And you get the lava comes up, it goes out, you have these vents. Same thing except it's just smooth flowing lava and you don't get the steep slopes associated with the ash falls. Okay, so what are the 2 types of volcanoes so far? Composite and shield. What kind of materials are in the composite? Okay, if you guys don't know this, you're in trouble. What kind of materials are in a composite? Okay, ash and lava. What kind of materials are in a composite? Let's try again. What materials are in a composite volcano? Okay, how about in a shield? Just lava. Alright, so what materials are in a shield? Just lava. This is where you have a lot of and hohoi hoi. Okay? These are typically quiet volcanoes. So if I asked you what's a quiet volcano, you would say Hawaii. You can even say Kilauea or Mauna Kea or all these different Hawaiian volcanoes are quiet eruptions, lava flows. They're not super explosive. Shield volcanoes. Okay, and the third type is a cinder cone. Do you guys remember this from the notes? The three types of categories of volcanoes? Well, cinder cones are just the pyroclastic ash and material. So the blocks, the bombs, and the cinders, and the dust and the ash. Okay? So, what kind of material is in a cinder cone? Just the ashes and things. What kind of materials are in a composite? Ash and lava. What kind of materials are in a shield? You see the three categories all neatly laid out there? Okay? These things don't get really big, and they're very steep. So this, I believe this is what grew into the farmer's field, a nice cinder cone. They make nice cone shapes. You see this nice cone shape here in the picture? Okay? This is in near Arizona. So here we have a nice shield, I'm sorry, I said shield. I'm sorry, a nice cinder cone volcano. Not the lava flows associated with the volcano, but just the ashes. Okay? Okay, and here's a picture of the composite volcano. This is Mount Shasta here, and this is Shastina. Okay, so here's the main vent that's come up like this, and here's a side vent that has started to grow a little bit on the side. This is in Northern California. So you can tell that a composite volcano, is it bigger or smaller than a cinder cone? Here's composite, there's a cinder cone. Which one's bigger? Composite. Okay? You guys have questions on the three types of volcanoes? Alright, let's compare the three. Here's that cinder cone in Arizona. Here's Mount Rainier, a composite volcano. And here's Mauna Loa. Which one's the bigger volcano? Which one's the, this shouldn't be hard. A, B, or C? A. You know that Mauna Loa is actually the largest volcano on the planet? It's not the tallest because it starts at sea level and below. Okay, but it's actually the largest. Okay. Whew! We are making some great progress. Almost done. Okay. These are volcanic features, so you could write down in your notes right now, volcanic features. Okay, features of a volcano. Calderas are one of them. Has anyone heard of a caldera?
Yes.
Okay, so the term is somewhat familiar to you. A caldera is simply a collapsed volcano. So this chart, I think, explains it really well. Here you have the magma chamber, or your full bladder, right? So the magma chamber is erupting. So here's Mount Mazama. This is in Oregon. Mount Mazama was erupting and erupting and erupting and erupting, but the magma chamber got so empty that there was nothing holding the volcano up anymore. All the pressure was released. So the magma chamber, it's like, I can't hold myself up. The mountain starts to, boom. The mountain collapses. It falls in upon itself, and it leaves the outer shell of the mountain. But the entire inner part of the mountain has fallen down and plugged the volcano. Okay, and in this case, that caldera, or the crater, was filled with water, and now you have Crater Lake. And well, Wizard Island is a new set. Now the volcano is starting to reform, so now the vent is now coming up in the lake. So yes, Wizard Island. So good job, Deja. Okay, so this is how a caldera is formed. So if I ask a question on the test, what is a caldera, you're going to say it's when a volcano collapses and leaves a bowl shape. Okay, the bowl-shaped crater of a collapsed volcano. Guys have questions on calderas?
No.
Oops. That's right. Okay. How much do I have left? Oh my gosh, thank goodness. Okay, I'm going to breeze through this stuff really quick because I don't want to keep you here anymore. Caldera. Okay, here's some volcanic hazards. I'm not going to let you write all these down. Big things. If a volcano erupts, get out of the way. Right? It can. This is, what kind of material is this?
Plastic.
When pyroclastic material flows like a river, you're in trouble. Okay? Pyroclastic material can flow like a river, and when it flows like this, it's called a pyroclastic flow. When it mixes with water, it's called a mudflow. Mudflows, you see how these houses have been buried? Okay, so here's a mudflow. This can do serious amounts of damage. Pyroclastic flows can do serious amounts of damage. There's a movie coming out right now called Pompeii. Has anyone heard of that? Pompeii is a city on the slopes of Mount Vesuvius in Naples, Italy. It was destroyed by a pyroclastic flow and an ash fall. So not only did the pyroclastic come down and wipe it out, and then it got just buried in ash. And then, here's what's even more genius. Let's build our city of Naples right up to the city of Pompeii, so now over 1 million or 2 people or more live in the shadow of a mountain just like Mount Vesuvius, which is still very active. Let's think about how genius this is. Okay. Yeah, I'll take a picture. Okay, so here's the pyroclastic flow. Moves like an avalanche, but it's not an avalanche of snow, it's an avalanche of fire rocks. Yeah, that's fun. Okay, the mud flow is often called a lahar. The volcanic ash can bury cities. Lava flows can obviously, if lava flows into your house, that's not a good thing. Okay. I'm going to hit this really fast, so go through the notes and look at this later. We don't get too much into it. If you have this full magma chamber, do you see how the magma chamber has all of these different little intrusions, so to speak, into the rock? You have flat intrusions and angled intrusions. The flat intrusions are called sills, like a windowsill is flat, and the ones that go across them are called dikes. Dikes and sills, remember that term from the quiz? Okay? Or this is where lava comes up and makes a little dome. This is called a laccolith, and when this is going to be a batholith. So, next picture, here's the batholith, a laccolith. The sills go this way, the dikes go this way. And if you have a volcano that's left over after a long period of time, and all the soft rock is eroded away, just left igneous rock is